and I would like to give you some information about matrices. Since we spoke about relation, we will speak about matrices defined on relation. So what is a matrix, first of all? A matrix is a rectangular object in which we have many entries, 1, 1, 1, 1, A12, A1M, and then A21, A22, A2M, and so on, AN1, AN2, ANM. Here we put...
Ho lasciato la destra della spalla, però non te la stacco perché sennò si stacca tutto, va bene?
Puoi staccarla e mettiamo la mia in parallelo. Sì, così. No, è che rimane, non c'è biscotti. Chiudi un momento.
Per non lasciarmi una pista qua, io ancora non sono andato. Grazie.
Okay, so we have this matrix is a rectangular object. In this case, is n rows times n columns. So n rows and columns. But one can ask, what are the entries? Aij in general is a number. So it can be a natural number, or a real number, or a complex number, and other things. We will speak also in the next part about finite field, what we show. So, are a collection, but nicely put in a rectangular form, and matrices has been used in many times from Chinese mathematician, some many centuries ago, and now they are a tool used in many things, in many areas of mathematics. Okay, our first application is consider a relation R. R is a relation. And for simplicity, just for simplicity, consider a relation in S times S. So where S is a set, so a relation can be obviously between two different sets. But for simplicity, this time we take on the same set, okay? And we say that S has other entries, S1, Sn. So these are the elements of our set. Now we can define our relation into a matrix in the following way. We say Aij, that is the entry that correspond to Ij in the matrix, can be either 0 or 1. And it is 1 if Si, Sj belong to the relation. So, for example, suppose that we have Alice, Bob, and Eve, Alice and Bob, Alice love Bob. In that case, it is 1. And it is 0 in the other case, otherwise. So, for example, I use the example of the nodes. Consider S equal to 1 to 3, and consider the matrix 1, 1, 1, 0, 1, 1, 0, 0, 1. So this is so-called a matrix A, in some sense related with the relation R. What is this relation? So, 6 to. So it is so it is satisfies when 1 and 1, 1 and 2, 1 and 3. Then it is satisfied with 2 and 2, 2 and 3 and 3 and 3. Is less than or equal to. So this is the related relation. So the relation is, so to say, the relation is this one, less than or equal. Obviously, good, nice relation give us nice matrices. What does it mean nice in mathematics? These are nice, something that is nice. That's beautiful. Beautiful things in mathematics are the things that are. So this is a clear, this is a triangle, upper triangular matrix of 1 and the other are 3, so hard to define. Obviously, if we go and if we consider this new matrix, okay, another matrix this way, in which we put 0, 0, 0. Here the relation is not anymore this, because it is not defined. It is not defined. Put, it is not good. So we have only the 3 related with 3, 2 related with 2, and 1 is related. So in this case, the relation is the equality. Okay? In this case, the relation is the equality. Pay attention that this matrix will be called the identity matrix. And see that really equal is something that says identity. And it behaves as the one number. But this we will show. Okay? So nevertheless, it is possible to represent a relation with matrices. Obviously, if they are infinite set. If they are infinite set, you need to have infinite matrix in the result. Okay, but for finite set, you can define the relation. So obviously, there are some interesting property because with respect to the properties of relation, we have the reflexive property, the symmetric property, and one can try to understand what happens in the matrix. So, for example, having the diagonal of ones means that one property is satisfied. Wow. Yeah? Yes, so everything is related with itself. Symmetry or reflexive? Reflexive. Okay? The reflexivity. The symmetric is if something is 1 here, The opposite is one over there. That is means that the matrix is symmetric.
In this case, it's both perplexity. Right?
So in this case, also symmetric. In fact, this is an equivalent relation. So it's one in the diagonal, and it is symmetric as a matrix. And one can see also that is transitive. This is much harder, but you can find that some kind of path and blocks. But nevertheless, this is not so easy. So nevertheless, I wrote this. In fact, I claim in the notes, if we focus on the equivalent elements to a given A by transitivity property, we have a submatrix all of ones. Here, the submatrix of all ones is continuous. Maybe we can have another picture that I put here. So here we have another starting set 1, 0, 1, 0, 1, 0, 1. This is symmetric. It satisfies the reflexivity, and moreover, this matrix is all of ones, submatrix all of ones. And one can see that this is an equivalent relation. In fact, one can see 1 is equal to 1. 1 is to 2 is equal to 2. 3 also may be related with. So 1 is related with 1, 2 is related to 2, 3 is related with 3, but also 1 is related with 3. So suppose that we have the set 1, 2, 3, and we partition into subsets the set of odd numbers and the set of even numbers. There is only one even number that is 2, and the other 1 and 3 are related. And this we already know by the previous lecture, it is an equivalent relation. Okay? But we can do much bigger example. To see a full submatrix of 1, you can focus on this matrix in which you remove this line. Then you have a full submatrix of 1. Or if you prefer, you can write the number in this way and make the matrix. Because S1, S2, S3 can be reordered in some way. So in this case, the matrix, exactly the same matrix of the relation becomes 1, 1, 1, 1, 1, 0, 0, 0. Here, you can immediately observe that we have the transitivity property. Here it is here. So a submatrix all of 1. This means that the transitivity property holds. Okay? We will give other example of matrices related to combinatorics in the next part, but in this chapter. Okay. Now, so we consider this matrix. Another object that we consider it the so-called function. And in my notation, I consider a function from A, where A and B are set. Obviously, in the part of calculus, you all the time focus on function. But are functions on numbers, on real numbers. Here we want to make a little bit of abstraction, or if you don't like the abstraction, you can think as a function on Alice, Bob, and B. Because it's something that maps A into B, where A and B are set, can be also the same. So, but what is a function? Using the symbol, we can write, I wrote in the notes, for all x, A, there exists an element x in B such that f of A, oh, excuse me, oh no, excuse me, yeah, for all A, obviously here, for all A in A, and for all B, and there exists an element B such that f of A is equal to. So a function is nothing more than a relation, but a particular relation. We are saying that A is related with B. So a function is a relation. So in this direction, it works. A function is a relation. The other direction does not work. Not all the relation are functions. So we are mapping an element A and we compute its image into B. For any A, there exists a B in B such that f of A is equal to. So a kind of correspondence. Example of function. Example of function. For example, we can say A is equal to B equal to the human being. So a person. So now we can say mother of A is B. So every person has a mother. Okay, so this is a function. Obviously also a father. Of course. Maybe it's hard to know what is the father, but mother, we are sure. Okay? We say in Italian this, answer in Latin, there is this rule of law. Father is always, if mother is always sure. So nevertheless, this is a function. So a function does not be necessarily a numerical function. Okay? Okay. Now, I want to show in the notes something that I try to represent in the notes. So we have here this representation of relation. A parabola is a relation, and the circle is a relation, and the line is a relation. Okay? Now we want to represent them as matrices. the following way. So remember the picture. We have the parabola that pass from the origin with the vertex on the origin. Y is equal to x squared. We have the circle and the circle and the identity function. Pay attention. So what I want to represent here, instead of consider all the real numbers, go through the discrete representation of this object. Instead of focusing all the numbers, we consider only the numbers -1, 0, and 1. Okay? A and B are -1, 0, and 1 in the real number. And then we intersect the relation with this A times A. What we obtain? What we obtain is that in the case of the identity function is -1, -1, because it's the identity function. 0, 0, 1, 1. In the case of the parabola, -1 squared is 1, 0 squared is 0, 1 squared is 1. In the case of the circle, we have these 4 points that satisfy. Remember that the equation of the circle is, here I want to remember you. In the case of the circle, we have x squared plus y squared equal to 1. Okay, so if we plug, for example, as x -1, -1 squared is 1, 1 and 1 is okay. What remains here is only 0. And the same obviously holds for 0, -1. But also it works for 1, 0, and 0, 1. Okay? So in fact, we have these 4 points. These 4 points. Now, we can represent this as a matrix in which we have -1, 0, 1, -1, 0, 1. For the identity function, we have the identity matrix. Oh, so nice. This is for mathematicians, it's nice. Because good properties of the matrices can be obtained by good properties of the function. Identity matrix, identity function. Remember that here we have -1, -0, 0, 1, 1. So it is defined, here it is satisfied only in the diagonal. If you remember what is the representation of the relation with the matrix, this is the matrix of the identity function. In the case of the parabola, is this one. Pay attention, the parabola in this way is the parabola in this way. In the case of the circle, representation of the circle, it is not anymore a function, because for a function, obviously, we can have only a 1 for each row, because otherwise it is not a function anymore. But pay attention, here we have 2 1, 1 here and 1 here. So a circle is not a function, also in the representation, in the matrix representation. And here I describe it. While the matrix induced by the other one are nice, does not represent function, because in the second row there are 2 1s. I like so much the representation because otherwise discrete mathematics, algebra is not so nice. But when you can show the picture here, the picture is exactly here. I'm considering as points the entry of the map. So this is the entry A11. So it is the matrix but rotated. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3, 3, 1, 3, 2, and 3. So no one of these three relations is satisfied in this point. Okay? The two of them is satisfied in 0, 0. Obviously, the circle not satisfied. And so on. So another way to consider metric is a function and the relation all together can be by net. For the people that remember the quadrics in the secondary school. Okay. I prefer here the notes because instead of making picture and so on, it's so easy. Okay, so how I continue here? So this is an example. This is the second example. So it is clear what is a function. Obviously, if you like, you can have other as an example also fx equal to. We don't like so much in this course, but we always work. So there are lots of functions. To be honest, in general, in the course of calculus, it seems that all the functions are from 1 to 1, where 1 is the real number and the other one is the real number. But one can define also some function that we studied, and is not written here in the primary school. In the primary school, you started to consider an operation, that is the sum. The sum between two numbers. But the sum between two numbers gives us one number. So we can define in the setting of the elementary school natural number, we have a function, the function sum is a function defined of n squared e to n, in the sense that we have a b natural number and we have a plus b as the resulting element. So this is a function. So open your mind. This is a function. Pay attention. You study the function at primary. And this is a function with the input that is given by two elements, and the output is one. We will call this as a binary operator. This function is a binary operator because it works with two. Obviously, also the multiplication. One can, using the Python or C, we can have 8 times. This is also, obviously, you can find many operators. Also infinite operators. Obviously, the ones that are more used are the one that comes from arithmetic. So this is not written in the notes, even if I will use in the future. Now, another concept that I will use, so that it makes sense, I want to define two functions, f from a to b, and g from b to c. Now, using my notation, I can consider an element since there exists a P such that f of A is equal to B, there exists B in B such that for all A in A, and also there exists a C in C such that G of B is equal to C for all B. So it is for any element put in here, we have an image here. For any element taken here, we have an image here. So from this we can have this mapping. Now, what we can do is to consider a new function that here we use this big dot notation. This new function goes from A directly to C. This is the composition of the two functions. That is, taking an element in A, if A gives us an element in B, G of B gives us an element in C. So the composition of function can be all the times defined if and only if we are mapping from A to B and B to C, where A, B, and C are fixed. Pay attention once again, we don't necessarily have to play with the real number, as in calculus. One can say, for example, what is a grandmother? Grandmother is a mother of a mother. So the composition of two functions give us a new function that is grandmother. And this is the composition of the function mother composed with the function mother once again. Obviously, you can also mix the things. This is the first stupid example that arrived in my mind, but you can do other more complicated things. So really, you can modelize functions that are not necessarily real, autonomous. Okay. Here I show you a numeric sample. So let A, B, and C are all equal and all natural numbers. In general, I don't use real. Right. And consider f of x equal 2 times x, and g of x, that is 3 times x. Okay, now you can see that g composed f is a new function that is c times x. Not so clever, but it is the composition one. If we take the one, and we double, and then take the same number, and we multiply by 3, then it is the same that multiplying by 6. Okay. So now that we have the one example, another example, we say that a function we say, yeah, f from A to B is injective. And here we use the notation, so to say that the mathematical notation. If for all A prime in A, so here, such that f of A is equal to f of A prime, then A must be equal to A prime. So if happens that FA is equal to FA prime, then the only possibility is that A is equal to A prime. Obviously, one can say, oh, Professor, I don't understand anything because of this definition. So we consider an example. How we can represent a function through Venn diagram. Okay? We can use this notation. Here is the set A, and here is the set B. Now we can use a kind of graph and make an arrow from an element A to an element B. This seems to be a nice representation of a function, because a function what do? Take an element and map to or and but pay attention. It is possible when we consider a function to have this. Okay? For example, if our function is y equal to x squared, here A is equal to 1, A prime is equal to -1, and they maps to 1. This is a possible function. We have many of these functions. Well, this function is not injective. Because if A prime, A and A prime are different. Nevertheless, they map to the same element. So a function to be injective must be of this shape. Here we have an arrow, here we have an arrow, here we have an arrow. It's not possible that two arrows go through the same elements. Maybe there are other elements that are outside. Surely all the elements that are here are mapped somewhere because of the definition of function. For any A in A, there exists an element in B, but maybe here there are others. And moreover, all the arrows are completely distinct. Is a representation. So now we go back to the definition. Now that we know the picture, we can understand really that we have a function from A to B, A and B can be distinct. Well, for all A prime in A, such that they goes to the same element, then necessarily A and A prime are equal. So try to represent things also by picture to understand. For you, the notation is important, obviously, but you are not mathematician. So maybe you cannot give a perfect definition, but it is necessary that you have a clear picture on your mind. Okay? Obviously, if you do both, you have a nice notation and also a clear picture, is marvelous. But remembering only this definition without understanding anything, it is very awkward. You cannot solve the exercise. Okay. So this is the definition of injective function. Pay attention that in my notes there is no Venn diagram, unfortunately. I need to find the time. make this picture. So maybe I also can write and the future next year. Oh, so I think the but you can find also. Um, in particular, in the example, I say F, G, and H are all injective. If you consider the example before, 2 times X, 3 times X, and C times X, these are all injective functions. When I multiply by something, K, then it is impossible that there are two elements that map to the same when we multiply by K in the natural number. And K is a natural number. Because if we do the same, no, this is always correct, yes, in any case. So the multiplication is nice, is in J. So what I claim here, I don't know if the claim is correct. From now on, we focus on two functions and the corresponding matrix of example 26. The example 26 has one of the parabola, blah, blah, blah. Parabola, identity function, and the circle that is not a function of. So the first function, E of X, X is the identity function. And P of X is the parabola, X square is another function. So the identity function E of X is injective. And P of X is not injective. A function is called surjective. So now we define surjectivity, surjective function. So we have a function from A to B, always. If for all B in B, so now we are considering the elements all B in B that exist an A in A such that F of A is equal to B. What does it mean? It means what is written. But nevertheless, if we consider A and B as a Venn diagram, here there are no orphan points. All the points are covered by some elements, not necessarily injective, but there are no elements here alone. So every element in B, so to say, is an image of an A. So there exists an element here in A, so that B is in it. For example, the identity function from A to A is also surjective. we want to write some example. Consider the function E, the identity function that maps from A to A is subject, where the identity function is nothing more than this. An identity. Other functions that are surjective, I put some example here. The function is surjective. P of x is not. P of x is not, but pay attention, we can do something. P of x is the parabola. What takes? Takes an element R into an element R, a real number. Okay? So one can say, oh, pay attention. P of x, if we have x squared cannot be never in R less than of 0. So all the elements that are negative. Okay? Here is the set of real number with A less than 0. Okay? This R less than 0 is the set of real numbers that are negative. So whenever we do the second power square, then we have a positive number. This cannot be. So this is not surjective.
It's subjective.
What?
The second one is subjective, the first one is not subjective.
The first one is subjective, the second one is not subjective. Not subjective. Because when we do the power x squared, we always have a positive number, never a negative. So it is not subjective, x squared. Okay. Okay, by the picture you see, no, if you have the parabola, and here we have x, and here we have y, the image is this one. It's not this one, never. So it is not subjective.
When we see P of x, we don't fix the domain. It's R in R. Yeah.
No.
So that way it's not subject.
Yes.
It's not subject. But when we say R below only less or equal to 0,
greater than or equal to 0, it becomes. In fact, pay attention. The observation of your colleague is correct. If something is not subjective, if something is not injective, it's hard to solve. We see a little bit. But if it is not subjective, we solve it in some sense. Because consider once again our parabola. This is a stupid operation, x squared. Okay. For example, we have 4, we want to know what is the root, we say, of a square. 2. Okay. And 9 is 3. So it is nice to make the inverse. So in some sense, it could be nice to solve this problem. How can we solve the problem? First of all, what we can do? We define this new function, P of x, a little bit better. First of all, R maps to only in R greater than or equal to 0. Then it becomes surjective just with this observation. Instead of saying that B is R, we say that B is R greater than or equal to 0. Do you agree?
so the purpose of this is to make it inversible.
Yes. Okay. Because it's so nice, it's important, resolving at least an equation of the degree 2. So instead of thinking of the previous function, we first say in B, pay attention, this is not considered. Okay. So first step. Nevertheless, nevertheless, this is not so nice because here, suppose that here we have a 1. I want to know where it comes from. One can say either from 1, but also from -1. Ah, no good. No good. So to make a function bijective that is injective and surjective, we need to do something. So we can solve it this way. We remove also this. And so this branch of the parabola can be inverted. It's just a problem solving problem, a problem that one has to solve. So don't think about mathematics, but you have a clear problem to solve. How can we solve? We want a function that is injective and surjective, so that when we have the image, we have only one element that comes from, but must be injective and surjective. And so what is the function that we consider? The inverse of x squared is the square root of x. So the square root of x, it is a compromise. It is not exactly the inverse of x squared, but it's a compromise. In fact, if you power on your calculator or smartphone and you put the square root of -1, it says, oh, error. Or if you want the square root of 1, he says as an answer 1, never -1. Because we want to consider, we focus on the branch, on the positive branch of the parabola.
Yeah, but shouldn't it be plus or -1?
But it is something that you plug. Because otherwise it is not anymore a function. Square root of x is a function only if the square root of x is defined on r greater than or equal to 0, mapping to r greater than or equal to 0. To solve this problem is something that you solve by strange rules that your professor try to explain you. But this is only the matter of making it invertible. And we have a big problem also for a stupid function that is x squared. So how can we solve? Well, we consider this function that is the inverse not of the parabola. This is not the inverse of the parabola, because from the parabola we kill this part and we inverse only this part. Okay. And is also important because now you are not old, but you are more than 18. So now you really have to understand why there are some choice in mathematics. Choice of mathematics are not random choice, are choice of a language that try to make our language more powerful. Is that so the people say, I don't understand mathematics. No, I don't, this is very technical, I don't understand mathematics. But we are full of mathematics. A child of 1 year old, 2 year old, pay attention. He starts to move in a world, three-dimensional world. Walk in this geometry, three-dimensional geometry. Oh, no, this is a step. I can do this. This is a priori in our brain. So we have a very wonderful mathematics that is inside. So anyone is a mathematician. The problem is that the notation seems hard to understand. But notation is a way to clarify the language. This is a problem of expression of mathematics, not of try to express your mathematics. Okay. So, okay, so this is the function. The function is called surgetti, blah, blah, blah. Okay, as I told you, a function that is both bijective, so a function that is both, if we have injectivity plus surjectivity, what we obtain is a bijective function, bijective. And this is very useful for mathematicians, but for all the people that try to solve problems. Because if we have a function that is bijective from A to B, then we can define the inverse function from B to F. And the nice fact is that F minus 1 gives us the identity function. And also in the other direction. We have once again, and this is the problem of making the square. So 2 square is 4, square root of 4 is 2. But using the assumption that we are mapping from positive almost 0 to positive number. So we solve the problem considering the part that is inverted. Okay. Oh, pay attention that if we use this notation in which A and B can be different, here we have to make a correction. Yeah. Because this is the identity in A and this is the identity that can be different. Can be different. It is not necessary that A and B are the same. One example, for example, consider so I try to write an example. We consider f of x equal to x, okay? Stupid function. In the natural number, into the natural number. If we multiply by 2, we don't have all the natural numbers. Do you agree? Because any times we multiply by 2, you skip 1. This is not good. So we call another object that we call n. I don't know. We call n2. Okay. Or maybe much better this notation. No, I prefer this notation. 2 I use this notation that is that makes more sense. Here we have a set. This set is 2n. The set 2n is defined this way. 2n is the set of 2. Or maybe we define this even number. 2n is exactly in the first part of our lecture 2e. 2, 4, 6, 8, and so on. Now this function is injective and it is surjective. So can be inverted. What is the inverse? F minus 1 is the function that we call in this way, is defined F minus 1 of A, is A of divided by 2. Do you like this notation? So whenever we have in this set 2n or even number, then this number divided by 2 makes sense, give us a natural number. Now, if we compose F composed to F minus A, F minus A is defined on 2n. Okay? So here we have an even number. So this even number is F times F minus 1A. That is, this even number can be divided by 2. So this is F times A divided by 2. That pay attention because of our choice, this is a natural number. And now we obtain 2 times A of H. And since this is a natural number, this belongs is A, that is an element of 2n. So the identity is in 2n, not in n. And if you go in the other direction, f minus 1 of f of A, here A belongs to n, a natural number. For example, 1. 1 times 2 is 2, 1, 2. 2 divided by 2 is 1. So here the identity function is E of n. Here is the identity of E, or if you prefer, n. So you need to make example to understand my notes, which is not so clear. Why one is the identity of A and the other is the So if A and B are different, you have two different identities. Okay? Here, not so much. But nevertheless, you can try to open your brain. Okay. Okay, I made also the picture of the parabola on my notes. And now I will speak about particular functions that are related with information technology. Okay. Consider this set F2, 0 and 1. We will see in the next chapter, in the next lecture, why I call this set F2. But this is the set of bits. Bits are important. From a wonderful work of Shannon, that is the father of information technology, he started defining that the information in these two elements, 0 and 1, and he called these elements bits. Okay? And they have very good properties. Okay? But what are functions that we can define? We said bits can be used to represent numbers. For example, the first fact is that any number can be represented in base 2. Okay, how can we represent? So we have a function, we have the natural number here, and we want to represent this number in F2K. What does it mean, F2K? One can say, oh, other notation. Professor, we are completely crazy. Every time new notation. Pay attention, this is a notation that we already defined because it is the Cartesian product of F2 times F2 times F2 times dot 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 times F2 K times. Oops. K times. K times. So this is a string of bits of length k. In particular, the string of bits is a tuple, is an ordered set. For the people that arrived here and knows how the computer works, in general, the representation of the memory of the of the computer is a block of 8 bits, and blocks of 8 bits are called byte. So they try the idea of Shannon, and byte is an byte. So we have, okay. So how can we represent 0 in base 10 is a string of zeros. 1 is 0, 1, or 1, if you prefer, maybe 1. 1. Pay attention here, the representation is the same. Then we have 2 in base 10. What is 2 in base 10? 1, 0. 1, 0. Perfect. Then we have 3. 1, 1. 4. 1, 0, 0. Okay? It's clear for all. So we can represent from base 10 in base 2 without any problem. And we use the standard notation that goes from left to right. Here are the bits that are less important, and here are the bits that are more important. This is nothing more than 2 raised to 2 times 1 plus 2 raised to 1 times 0 plus 2 raised to 0 times 0. That at the end is 4 in base 10. So one can do this representation. For example, in the notes I wrote, what is this number? This number in base 2 becomes 1 times 2, 0, 1, 2, 3, plus 1 times 2 raised to 2, plus 1 times 2 raised to 1, plus 1 times 2 raised to 0. That is 8 plus 4 plus 2 plus 1. That is. Okay. Sometimes I use some exercise that plays also with this object. Okay, so this chapter is from technical to mathematical. There is something strange. So consider now this function f of x that is equal to 10 raised to x. One can observe that since we are playing, we have 10 fingers, this is the only motivation because we use base 10. With 2 fingers, maybe we will obtain it. Okay, but since we have 10. So, but now we observe that anytime if x if this function is from the natural number to the natural number, here what we have. The table is easy. So here we have the function, here we have x, and here we have the function. Or, okay, maybe we start with which one. 1 is 10, 2 is 100, 3 is 1000. And this is an interesting property in information technology, but also in the primary school, we say, oh, very easy compute this computation. Why? Because the only thing that we use is the so-called shift operator. The shift operator is often used in informatics because it's a stupid algorithm. You just shift and put it 0. Okay? But now, this is base 10, but this is base 10. This is in base 10, because it's this 10 in base 10. But if we want to play on our computer, the bytes and everything is in base 2. So, if we do the same in our computer, now the function with the shifting operator is 2 raised 12. Okay? So, for example, here we have 1, 1, 1. Okay? That in base 2, we observe is if we have 1, 1, 1, 1, 0, okay, with another 1 again. What is this number? In that case, was multiplying by
31.
30. Because we are multiplying by 2 instead of by 10. Pay attention. This is 2 raised to 0, 1, 2, 3, 4. 4 plus 2 raised to 3 plus 2 raised to 2 plus 2. Do you agree? Because there is no plus 1, since this is the so this is 16. This is 8 plus 4 plus 2. 16 plus 8 is 24, 28, 30. And this makes sense because in the previous case, shifting and putting a 0 means multiplying by 0, multiplied by 10. Here we are shifting in the word of bits is multiplying by 2. Okay? So in many programming languages, there is the shifting operator, for example, C, Python, and so on. But when you deal with the shift operator, this is the shift operator in bits. So if you reconvert the number, you are multiplying by 2, or if you shift in the other direction, dividing by 2. But pay attention that the reminder, you lose the reminder. So, for example, if you do the shifting operator of 15, then the resulting is 7 and not 7 point something. Okay? Do you agree? Shifting in the other direction 15, you lose the last number. Okay? If you have 15 and you shift in the other direction, in this direction, then you lose, you obtain this. But in fact, 15 divided by 2 is 7 something. And the something in general is only a technical fact. This is the shifting operator in this direction, and this is the shifting operator in the other direction. C and Python use the same notation. Okay, Python copies C. Because I remember that C has been defined by Dennis Ritchie in 1970. This is wonderful because after 54 years or more, it is almost the same language. This is a wonderful because for all the many languages passed and they who knows Pascal, Fortran, Copol, no one knows. But C remains almost the same. So the notation is wonderful. Also in this case, because I liked very much programming languages. In the first course that I did 3 years ago, I tried to use also Python, but then I realized that it's impossible for you in general. Okay? This is why I put in this chapter is this strange function. But nevertheless, they are interesting. Okay. To finish this part, I want to focus on this function, and we'll consider this function also an extension of this function many times. So consider that we have any of these functions, a function that goes from F2 or F2. So in the world of B, we have a function that has as an input a 0 or 1 and has an output 0 or 1. How many are these functions? We have only 0 and 1 here and only 0 and 1. 4. 4. No, sorry. Yeah. Okay, we can represent. So here we put in my notes is written this way. So here we have the so-called the domain. And then the image is the codomain using the calculus. So here the domain is 0, 1, always for here. Here we have, for example, the first function that we can define is the constant function that gives us as an output 0. Is boring function, but there is the constant function 0. Yes. So we call this function using my notation. Oh. Okay, using my notation, okay, it's not important my notation. We call this function, I use another notation, okay, I don't like it. So this function we call, for example, 0, that give us 0, 0. Okay. But also another function that you call 1 that says 1, 1. I don't care what is the input. I always give us an output 1. It's a constant. But then there is the identity function that says 0 and 1. And then the, so to say, the opposite function, maybe minus I, don't know how to call it, minus I, or maybe I opposite, that is 1 and 0. 1 and 0. Pay attention, there are no other. If we have a function from F2 to F2, the codomain, since we are considering discrete mathematics in the finite set, we can define all the functions. Maybe there are terabytes of function, but they are finite. In this case, there are only 4. The constant function 0, the constant function 1, the identity function, and the so-called opposite function. Okay? So this is a way to play with function without obviously considering real number geometry. And they are studied in information technology, but also in mathematics, this kind of function, especially in the last 50 years. Okay. So this is a constant function, 0. This is one function. This is the identity function. This function has a name in information technology that called the not function. Not that. If you use some programming language, it makes a kind of logic interpretation, because one can think 0 as false and 1 as true, and in this case, this is the function that always say false, like a stupid baby that says to all your questions, no, 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 no. Some child will say, no, no. So this is the stupid child function of no. The very nice guy, like some Indians, no? Some Indians, you ask to an Indian and say, yes, I can do, yes, I can do. Maybe sometimes he doesn't do, but since he is polite, he say always yes. So this is the Indian function, yes, 111. So the Indian people that are here, we know. Okay, so the identity function that is also a little bit boring, that is a kind of mirror, 0, 0, 1, 1. And also the other one is the not function, that is exactly the opposite of what you say. This is a really unpolite person. You say yes, and he says no, so he's unpolite. An Indian person. Okay. So these are the very nice, interesting four, the easiest function in the world of mathematics. Okay. Yes. Yes. Um, okay. Now we finish this chapter considering the operators only. We remember that function can play either on the set A, but also in this case, for example, on F2 times F2. So on 2 bits, not only one, 2 bits. And here we have an operator, like the sum. So we have F2 times F2 in F2. We can do this, yes. How many are these functions? This time the functions are the class of functions, so the set of all the functions of this type. So the cardinality of the function, we can call this F. All the function, so the cardinality of the function F such that F goes from F2 to F2. How many are there outside? There are exactly 16. Okay? So there are 16 operators. 16 operators that by starting from 2 bits, we have another bit in output. Is it clear? Obviously, the 16 operators are not so, many of them are not so interesting, but nevertheless, if you want, you can enumerate. Here, I just want to show you the nicest one. So here as a domain, we have F222. So in information technology, we write 0, 0, 0, 1, 1, 0, and 1, 1. Pay attention that the mathematician in this case represent as a double, a pair, okay? So this is a synthetic way to write an element in F222, okay? But here the mathematician in our brain is an element of the Cartesian product, so 0, 0 as a pair, okay? What is your question? No, no, what is your question? And the order is not so important, but nevertheless, this is the best one. Why? Here this is 0. Then we have in binary representation, in the decimal representation, this is 1. Then it is 2, and then 3. So this is the more standard representation. Obviously, you can swap some of them, but it's not so nice. If you count from 1, 2, 3, 0, 1, 2, 3. So this is the default order, so to say. Obviously, if you think as an element of 2, to be honest, this is not the right representation, but the representation is 0, 1, with parentheses, 1, 0, and then 1, 1. Pay attention, these are not sets, are ordered elements, because are elements of the Cartesian product. So the order is important. This coordinate 0, 1 is different. This point 0, 1 is different from this point 1, 0. Okay, the order is important. Now we have 16 operators. The first operator here, I use the logical representation. The first is the OR operator. So false or false is false. False or true is true. True or false is true. True or true is true. So this operator has a lot because it solves exactly what happens in the case one thing is true or false and the other one is so something that I will become wet if it is rain, if outside raining, and or I go to the shower and take take a shower. So in this case, this operator has really logical. So here I express only some of them that has some sense. Another one, oh, pay attention, this is strictly related with the previous lecture when we spoke about the union. In the case of union of two sets, something is true if it is satisfied in A or in B or in both. So things as the set, or not only as a set of elements, but properties that a set defines. Okay. In this case, the OR is strictly related with the union. Some people in mathematics use also this symbol. In fact, it is very similar to you. Another one is the XOR. XOR is related, is the so-called exclusive OR. Is exactly equal to the OR with the only one exception, that is the last one. If both are true, then it is false. This means that we are exactly in the symmetric difference case. So XOR is, so to say, connected with the symmetric difference. Is it clear? Another one is AND. AND is true if and only if both input are true. And these are obviously a logic. So if both things, so if I go outside and it's raining and I don't took my umbrella with me, I'll become wet. So in this case, we have the intersection. The connection is the intersection. So this is the intersection, and some people use also this symbol. Nevertheless, if you use programming languages like Python, you use OR, SOR, and AND. In C, if you like, you use a double bar. So is this one, and then it's double ampersand. So they are so important as operator of bits. You don't have to have a particular comma. So within the 16 possible operator, only these three ones have a name. Okay? The not, pay attention. What is the difference between OR and SOR and NOT? It is also not an operator. Why it is not here?
I guess. No,
Not.
it inverts the and.
No, not alone is a unary operator. Not was in the previous page because it's unary, it's not binary. Everything has an input, either only one bit, and give us an out one bit. Here in the input, we have 2 bits, is an operator. An operator on 2 bits. Or, sorry, and then not is an operator only 1 bit.
Not if I was in the bathroom and I see the other.
Yes, the not was this one. Not is this one. And as an input has only 1 bit. So it's a unary operator. While the other one are binary operators. And this is strictly related when we do a kind of operation like minus x. Unary operator, we have an element, a natural number, and we make negative in the integer number. We are doing the opposite. So as a kind of arithmetic meaning. Clear? So I want to make a bridge between information technology and algebra and arithmetic. But this minus is a unary operator. Just make it the opposite. And there are many of these unary operators. For example, if we have x, we map into 1 over x. This is another unary operator. Make the opposite. Inverse. So here there is really a difference between because in the previous case the domain was F2. Here the domain is F2 squared. Okay, so maybe we can stop here. You have any question? You tried to read the previous lecture and the examples. Did you try? No. You enjoy sleeping during the night instead of studying. Sometimes. Oh, so bad. But nevertheless, really, it is important to read the notes and ask everything if you have any problem. So on Monday, we'll have only 2 hours, not in the afternoon. And we'll surely next week, we'll finish the first chapter. So we'll do some extra exercises. Nevertheless, try to ask me as much as possible. Because then you'll be alone. In 1 hour, you'll have to solve the exercise. You're alone. Right?
Are there any updates on the programming feature?
I don't know. But I think if you have a kind of, you are inserted in a Telegram group, as soon as there will be an update, we communicate there. Okay, see you. See you, bye.